Hi, everyone. Thank you for joining us for Advancing Data Center Security with NVMe-oF technology. We will get started in just a few moments. Thank you. Hi, everyone. Thank you again for joining us for Advancing the Data Center with NVMe-oF technology. I'd like to take a moment here just to introduce you to our speakers. So we have David Black, who is a Senior Distinguished Engineer at Dell, and then Claudio DeSanti, who is a Distinguished Engineer at Dell Technologies. And with that, I'll go ahead and pass it off to the speakers for them to start presenting.
Thank you very much, Megan. So we're going to be talking about some recent advancements in NVMe-oF security technology, starting with the SAN security framework. Then we'll talk about the security protocols that have been part of the NVMe standards, and finally focus on the recent security updates in TP8018, which updated how TLS works with the NVMe TCP transport, and TP8025, which is about usage configuration of security. So let's start with the SAN security framework. So this is a storage area network example. On the right side of the screen, there's a large storage system that's providing storage, red, blue, and green storage to the red, blue, and green servers on the left side of the screen. They connect with some sort of fabric or network, which is shown by the cloud in the middle. And there's a management station or console that is managing all of the connectivity in addition to the storage system. So with this as a foundation, let's talk about the security threats to the servers accessing storage over this network or fabric. The first one is management and system integrity. And this is threat number 0, because if you don't get your management console secured, nothing else matters. The second threat is uncontrolled storage access. The red server could go in and just go straight for the blue storage. Not supposed to be able to do that. Then we have impersonation. The green server decides it feels like being blue today and accesses blue storage as if it were the blue server. This is sometimes called spoofing. The third threat is this nefarious character comes along, gets access to this whatever this cloud is, and is able to see and perhaps modify all of the traffic going back and forth between the servers and the storage. And finally, the storage itself might grow feet and walk off with a little bit of five-fingered help from somebody. Media theft and other access all fall into this threat category. So with these as threats, let's talk about what the countermeasures are. For management and system integrity, we simply need to put a stop to it. And there's two classes of putting a stop to it. The first is you need to have security for all the management and configuration interfaces, authentication, authorization, logging and anomaly detection, and all access to management systems and by management systems needs to be done with secure channels using a security protocol like TLS. The second class of countermeasures is system integrity, hardware, software, and firmware integrity of the management station. In fact, all the components shown on the screen with checks and assurance, preferably anchored to hardware roots of trust in each case. Okay, second threat is, number 1 now, is uncontrolled storage access. The red server just goes and gets access to the blue storage. This problem has been understood for a very long time, and you essentially put up a screen which says only blue can get to blue storage. This is NVMe namespace mapping for mirror fabrics and NVMe fabrics zoning. Both contribute to putting up the blue screen and ensuring that the red server can't just go and access the blue storage. Well, that's nice. We get to impersonation. If the green server feels like being blue and looks like blue to the blue screen, the access controls, it goes right through. So for impersonation, the countermeasure is authentication, which is proof of identity. In essence, we require the blue server to prove that it is blue before we will allow it through the blue screen. The green server cannot prove that it's blue. It's green on the slide, you can see it. And since it can't prove that it's blue, it won't get allowed to the screen, and this mechanism blocks it by tying the access controls to the authentication or proof of identity. Third is our, hang on, here we go. Third is communication access, where this character shows up and is accessing the traffic in flight between the servers and the storage system. And here the countermeasure is secure channel, where we encase the traffic in flight in some kind of security protocol, such as TLS, that provides both confidentiality and cryptographic integrity for the traffic, so that our nefarious character at the bottom of the screen only sees encrypted data. He or she or whomever doesn't get to see the actual data of interest because it's been encrypted. Finally, we have the external access threat, where the data or the system just grows feet and walks away, media theft or other access. And the countermeasures here are generally stored data at rest encryption, so that if a component containing data is stolen, what's on it is encrypted data or ciphertext. NVMe Fabrics technology is about data in flight. We don't deal much with this threat. This is dealt with elsewhere via encryption in some component. It could be the application, server operating system, a hypervisor. For example, there are hypervisors that provide encryption for the hypervisor, and it could actually be the drive itself has onboard encryption, so that what is stored on the media is in fact encrypted data. Okay, so quick security review of the various elements of security technology. We have management and system integrity to put a stop to access through the management channels. We have storage access control that ensures that a blue storage, in this case, is only accessible to the blue server. We have authentication or proof of identity that prevents the green server from deciding it feels like being blue today. Secure channel, which prevents access to data in flight. And stored data at rest encryption. Because this is an NVMe-oF Fabrics talk about storage networking, we're going to focus on the network mechanisms, numbers 2 and 3, authentication and secure channel for data in flight. And with that, I'm going to turn you over to my colleague Claudio to talk about NVMe-oF security protocols, starting with authentication.
Okay, thank you, David. So, after David nicely presented what are the threats that we find in a storage area network and how we can counterbalance these threats, let's see what we define in NVMe Express in terms of protocols to really implement these countermeasures against the threats. So first one is authentication. This shows how authentication is implemented in the way in which a host and a subsystem, a host and a controller, set up their association, their connection, when they basically begin their dialogue and storage communication. Let's consider as an example NVMe over TCP. So we begin with an NVMe over TCP transport session establishment. Then we have the connect command is performed to set up the NVMe queue and associate the host to the subsystem controller. At this point, we have the authentication transaction, whose purpose is to, as David said, is to verify the identity of the two endpoints. The controller wants to verify the identity of the host wants to verify the identity of the controller. And once the authentication is successful, queue will be ready for subsequent operations. So, what did we define as the authentication protocol for NVMe-oF? It's called DHM matchup, fairly mouthful word, but why it's done in this way, we will explain. It's defined in the NVMe 2.0 base specification, formerly in TP 8006. The way in which it works, an NVMe entity, either a host or a subsystem, is provisioned with a key. which is a secret quantity, fundamentally a secret random number. And the purpose of the authentication, you authenticate your party if the party demonstrates that it knows its own key. So the host is authenticated by a controller if it demonstrates that the host knows its host key, KH. And a controller authenticates to a host by demonstrating that it knows its subsystem key, KC. That's how you demonstrate your identity. And what is the demonstration of the key knowledge? We use a CHAP protocol, Challenge Handshake Protocol, which is augmented by an HMAC function to compute the responses and a Diffie-Hellman exchange. That's why we have this mouthful word. The key, the fundamental information here is that the key is not passed in the protocol messages. It remains a secret. So the way in which the protocol works, the authenticator, as an example, the controller, sends a challenge to the host. The responder, as an example, the host, computes a response using its own key. As an example, the response that we can see here is the HMAC using the key of the host as a key of the challenge concatenated with other things. At this point, the authenticator verifies the response. This is the general way, and this is done twice. It's done by the controller to authenticate the host and by the host to authenticate the controller. We call this bidirectional authentication. Once a response is sent back to the authenticator needs to verify this response. This requires the key of the responder, and so the authenticator, as an example, the controller, will compute the expected response R1, R prime, and verify if the received response is equal to the computed R prime. Let's see how this works with some simple diagrams. Okay, we begin here. Host and controller. First step, as we said, is the key provisioning. We need to provision the host with the key of the host and a verification key of the controller to verify, yes, the controller is really the controller who is claiming to be. The controller will have its own key, KC, and the verification key of the host, KH. First step, the protocol begins with an auth negotiate message, in which basically sends a bunch of parameters to the controller, say, hey, I would like to authenticate, we can use the DHMACH protocol, and I support this list of hashes, this list of Diffie-Hellman groups. At this point, the controller selects the hash that will be used, the Diffie-Hellman groups that will be used, and sends fundamentally the challenge C1 to the host and a Diffie-Hellman parameter. The host now will use everything that is there, the Diffie-Hellman parameter, to compute a session key. This session key will be used to augment the challenge that has been received by the controller. At this point, the response R1 to the challenge C1 will be computed using the HMAC function, using the key of the host as the key, plus that quantity, the augmented challenge, a sequence number, transaction ID, protocol flags. The interesting thing is that this response also includes the identities of the two parties. This basically guarantees that there is no way for a third party to get a response from a previous transaction and try to repurpose for a subsequent transaction. At this point, when the R1, the response to the challenge C1 has been computed by the host, is shipped back on a DHMACH reply to the controller. And the controller has to perform the verification function. It has to do exactly the same computation as the host did, using the verification key, KH, at this point, which is the same as the host key. And so, in this verification, at this point, the controller computes the expected response, and if the expected response is equal to the received response, then the authentication is successful. If not, the authentication is not successful, the communication is interrupted, because it means, okay, I'm not connected to the entity that I thought I'm connected with. On the other side, we can see that the host on the reply can send a challenge CTO in which is trying to challenge, to verify the identity of the controller. So the controller will perform exactly the same computation to compute a response RQ to the challenge CTO. This will be sent back on a success message to the host, and the host will perform again the same computation to compute the expected response R2 prime, and then will verify if if the received response is the same as the expected response. If yes, this authentication is successful, otherwise not. And here we suppose that we are in a yes case, and so we will have a success queue that is coming. So this is the way in which we perform authentication. So authentication means verify the identity. To verify the identity, we verify, hey, do you know your own secret key? That's the way in which the protocol works. What is the problem? As we saw, if we look at a fabric which I have n host and m subsystems, I need, per each subsystem, I need to have my own key to compute my responses and all the keys of the host in order to verify the responses from the host. The same is true on the other side of the wire for the host. Each host needs to have its own computation key and all the subsystem verification keys for all the subsystems it could connect. Because only in this way the host will be able to compute the expected response in order to verify if the received response is the right one. This is complicated because it means there is a lot of provisioning that is needed for this protocol. And this is something that, as an example, has been seen as a fundamental problem with early implementation of the CHAP protocol, as an example in iSCSI. So we developed a way to resolve the problem. We call it authentication verification entity. What is an authentication verification entity? It's just a service in the fabric that can be accessed through a secure channel. And this service by all the entities in the NVMe-oF fabric. And this is just a service that has a complete database of the NQN, key records for hosted subsystem. In NVMe, the NQN, the NVMe qualified name, I forgot to say before, is the identity for an NVMe-oF entity. And the key is what is associated to that identity. So this is what an AVE is. And how does the protocol change once I deploy an AVE in my fabric? Everything stays the same. Everything needs to be provisioned with a key. The authentication is still that you need to demonstrate that you know your key. In order to demonstrate the key knowledge, you use a challenge response protocol. The only thing that becomes different is how you verify the response, which is not anymore computed locally by an authenticator, but is delegated to the AVE. This is analogous to the radius functionality that has been defined for iSCSI CHAP authentication verification. And of course, as I said, requires a secure access to the AVE, providing confidentiality and cryptographic integrity. TLS is a perfect protocol to obtain this result. So how does an authentication works between a host and a controller when an AVE is deployed? First, we have a change in the provisioning step. Now, when I do my provisioning, I need to provision on the host, the key of the host, plus a way to access the AVE. On the controller, the same thing, a key for the controller and a way to access the AVE. The AVE, of course, will have, as an example, the record NQN of the host, key of the host that I'm considering here. The first part of the protocol then is exactly the same. Sorry, nothing changes. The host sends an out negotiate, we get a challenge back with a challenge C1, the host computes a response R1 that is passed to the controller. Once the response R1 arrives to the controller, this is what the control was supposed to do. Compute the expected response and verify if the received response is equal to the expected response. Instead, what the controller does is send a request to the AVE to perform this authentication verification. And in this request message, auth request message will basically say, hey, I'm talking with host having identity NQNH, I'm controller with NQN having identity NQNC. These are the parameters of my transaction. This is the augmented challenge I received, and this is the response R1 that I received. Is this correct or not? And what the AV will do, will look up the key of the host from the NQN of the host. We look up this record using the NQN of the host as a key to locate the record, figure out the key of the host, use the key of the host to compute, to perform exactly the same computation, determine the expected response, verifies if the expected response is equal to the received response, and if yes, we are done. Is success, otherwise no. Same on the other side. The controller receives a challenge CTU, compute a response R2, send the success one to the host, the response arrives to the host. Rather than performing a local computation, the host asks the AVE to do the verification for itself. The AVE look up the key of the controller, perform the verification, computes the expected response and verifies if it is equal to the received response, and if yes, we succeed. How this, let's look at how did we simplify the provisioning thing. Well, everything I need now for a subsystem in the entire fabric is my key and a way to access the AV. I don't need anything else. And for every host, that is exactly the same thing. I need my key and a way to access the AV. And let's look at an example to see how this really resolve the situation. Let's consider a fabric with 100 hosts and 25 subsystems. And suppose that all hosts want to authenticate all subsystems and vice versa. So, how would it be an initial host provisioning? If I'm using just plain DHL matchup, I need to provision each host with its own key and all the 25 subsystem verification keys. If I am on DHL matchup plus AV, I need to provision the host with its own key and a way to access the AV. What happens if I add a subsystem to the fabric? I need to re-provision all my 100 hosts to add the additional subsystem verification key. This is the heavy part. Every time I change my fabric, I need to re-provision my hosts. If instead I have an AVE, I don't need to touch any host. I just need to add the additional subsystem key to the AVE. That's it. That's why the AVE is a powerful addition to the protocol. Same thing on the subsystem side. If I use initial subsystem provisioning, plain DHL matchup, I need to provision each subsystem with its own key and the 100 host verification keys. If I use the AVE, each subsystem needs to be provisioned with its own key and the way to access the AVE. When I add a host with plain DHL matchup, I need to re-provision all the subsystems. If I have an AVE, I don't need to touch any subsystem. I just add the additional host key to the AVE. In other words, once I deploy an authentication verification entity, now my DHL matchup protocol becomes scalable, the provisioning is scalable, and so it becomes effectively deployable. And go to the next step with David.
Okay, thank you. So I'm going to talk with Claudio. Talked about authentication and authentication verification. I'm going to talk about the secure channel protocol that protects traffic in flight from eavesdropping and tampering. NVMe fabrics for NVMe TCP chose to adopt TLS, specifically TLS 1.3. And the basic structure is shown here. The first thing that is done is a communication channel is set up, and this is set up with TCP using TLS, so that the connect command that is set in step 2 that is used to start setting up queues. In this case, you get one queue per connection. The connect command is sent protected by TLS, and with the secure channel and the queue set up, you show step 3, we're ready for subsequent operations. So this sequence on the slide is repeated per queue, so that it will be run through at least once for the initial admin queue, and then once for the IO queue, and then additionally for each additional IO queue that is created. And this is up to the host or server to decide how many IO queues it would like. So need to get into a little bit of details of what we're doing to authenticate TLS, because TLS requires authentication credentials. You're used to seeing TLS in the web or internet use certificates, specifically X.509 certificates. NVMe over Fabrics does not use X509 certificates right now, and the major reason why is that the identity in the certificate, the name of the host or the storage system, really needs to be an NVMe native identity. The reason is that NVMe supports non-IP transports such as Fiber Channel and InfiniBand that don't directly use web or IP identities. And at some point in the future, we're anticipating SPDM-based certificate authentication across all of these transports, not just the TCP transport where we're using TLS. So the upshot is that NVMe certificates should use NVMe native identities, which are NQNs, NVMe qualified names. These are text strings similar to iSCSI IQNs, which are iSCSI qualified names that are identifiers for that protocol. Now, a reminder of some things that are going on here. Certificate, the whole point of certificate is it cryptographically binds the identity to the public key with the binding signed by the private key of the certificate authority that issued the certificate. It is possible to use X509 certificates that don't contain the actual identity of the endpoint. You wind up doing mapping, but mapping the certificate identity to the actual identity of the endpoint weakens security because the mapping is not signed. So for all these reasons, the right thing to do is to use an NVMe-specific X509 certificate format that enables NVMe NQNs to be used directly as certificate identities rather than trying to reuse existing certificate frameworks. And that then gets us into the second set of concerns about use of certificates, which is certificate lifecycle management, issuance, revocation, and replacement. In the first part of this slide, there was a mention of a certificate authority. Well, that is in essence, a service that creates and issues certificates, and that has to be operated by someone or some entity. And so that's the first question here: who operates certificate authorities? The answer for NVMe is going to be vendors, including OEMs such as Dell and HPE, and device vendors, Samsung, Kioxia, Seagate, and others who produce SSDs. And that's not how the certificate authorities are operated that issue certificates for the web. If you want a certificate for example.com, you can go to one of a number of certificate authorities who will issue a certificate for example.com. An example here is an example, substitute your own domain. So we need to have an ecosystem in which the certificate authorities are operated by the vendors. PCI Express is already blazing a trail in this area. They have a PCI Express specific certificate format that uses PCI identities, and NVMe chose to watch, wait, and learn so that hopefully we can do something similar and not have to do major reinvention in this area. Okay. So the TLS credentials at NVMe, and here it's NVMe over Fabrics over TCP, is using on pre-shared keys. So in order to communicate over TLS, you need to provision the two entities with the same pre-shared key. Each pair of entities should really be using its own pre-shared key, which limits the consequences, sometimes informally called the blast radius, of compromise of a PSK. This creates a problem that you've seen Claudio talk about earlier, where we have an n-squared problem. On a fabric with n hosts and m subsystems, you have the product, or n times m PSKs that need to be managed. So what we do instead is we bring the DHH-MAC CHAP authentication protocol for NVM Fabrics to the rescue. as part of the DH portion of DHH MacChap, there is what cryptographers would call a key exchange conducted. So that means that upon successful completion of the authentication DHH MacChap, you can generate an ephemeral shared session key on the fly. This is where you get the pre-shared aspect of the key, and TLS negotiation is then performed using a PSK for TLS is derived from that shared key. There's a bit of mechanics in here because what happens is typically the ephemeral shared session key is rather large, and there needs to be some hashing and key derivation done to produce a PSK that TLS can use. But the upshot is that TLS PSK provisioning gets reduced to a per entity DHH MacChap secret provisioning. If you can do the provisioning as Claudio has described in the earlier slides of DHH MacChap, then DHH MacChap itself can be run to generate the required PSKs, and we haven't made provisioning any more complex. And the upshot is that when the AV is deployed, we have only an order of n problem. A fact with n hosts and m subsystems only requires n plus m secrets, the sum, not the product. So this leads to the original TLS concatenation design, which is that we set up a TCP session without TLS, connect up the admin queue, run the authentication transaction, step 3, generating a PSK for TLS, run TLS over that TCP session, using the PSK to authenticate this TLS secure channel. And now we have the secure channel and the queue set up, and we've done authentication, and we've done TLS. And this is how we sort of leverage DHH MacChap to get not only the authentication of the endpoints, but also setup of a secure channel. And with that, we've now completed the background material, and we'll start talking about what has been recently done to update and improve NVM fabric security, starting with what's been done to improve the use of TLS with NVMe TCP. I'll turn you back over to Claudio.
Okay, first point, how does it happen that how do you set up a TLS connection using a PSK, which is what David just described? The host that begins the TLS setup, or anyway the client in TLS terminology, sends a client hello message to the server, that would be the subsystem in this case, or the controller. And in this message, basically, this message is over TCP, so is not encrypted yet. And in this message, the client says, hey, I would like to set up a TLS connection over this TLS session, and I would like to use this PSK. The PSK that is specified through one PSK identity. And so there has to be a unique PSK identity that identifies a PSK on the server. Now the server gets this PSK passed on the initial message, PSK identity, the initial message, look up from this identity the proper PSK, and at this point say, okay, let's use this PSK, and now I begin to sign my next message using that PSK. So only if you, client, know the same PSK, you are able to go ahead with the protocol. That's basically how the TLS setup goes through using the PSK. So the first step is I need a PSK identity. And you need to be sure that you have the PSK identity uniquely identify a specific PSK that you need to use for your channel, for your TLS channel. So in NVMe TCP transport, we define two methods for obtaining a PSK. One is what we call the retain PSK from an administratively provisioned configured PSK. So an administrator just manually set up a PSK on a hosted a subsystem. Okay, we call that a retain PSK. But then David also said, oh, we can generate a PSK from the DHH MacChap authentication transaction. And so we call that one a generated PSK. So we have these two ways in which we can define a PSK between a host and a subsystem. And then, as I said, we need a PSK identity that enables to uniquely identify a PSK between two entities. And so we defined two associated PSK identities. And we basically used these ASCII string as the identity to look up. NVMe 0 means is format 0. R means it is the retain PSK. This is the hash function associated with this PSK. And then I basically use the concatenation of the two identities, the identity of the host and the identity of the controller, the two NQNs. This is basically the retain PSK. And the following one is the generated PSK. The difference is really the R versus the G. Otherwise, the format is the same. R for retain and G for generated. Great. Okay, the scope of retain PSK was fairly clear. You say, well, I set up a generated PSK. I set up a retain PSK between a host and a subsystem. Okay, every TLS session that I will set up between this host and this subsystem will use that single retain PSK. Fairly straightforward. It was not very clear what was the scope of a generated PSK, because we started thinking that, oh, this will be per queue. And if it is per queue, in a sense, the things can work, because for every queue in NVMe TCP, we have a different TCP connection. And so now the TCP connection can be used to disambiguate if I have multiple generated PSKs between a host and a connection. And then we say, well, we can reuse what we generated on the admin queue on the IO queues. And now we are beginning to share the PSKs. And what is the problem? Again, you have we are getting in a situation in which each DHM matchup transaction generates a PSK. But I need an identity that enables me to identify that PSK. And I define only one identity. So in reality, having defined only one identity between host H and controller C means that I can have only one generated PSK. But I can generate many. You understand where the problem was. We did not define well the scope of a generated PSK and how to identify it. The scope that everyone liked and would like to do was, okay, I do my TCP handshake, my connect, my DHM matchup on the admin queue. The DHM matchup generates a PSK, also does a TLS handshake for TLS concatenation as David described, and now I have my admin queue became in TLS. And then use this generate PSK to do a direct TLS connection. So TCP handshake, TLS handshake, connect, done. I'm already in TCP. And all the IO queues just leverage these generated PSK kind of global between these two entities. But we want to support also the per queue scope, which basically means, well, I could do in each queue a TCP handshake, my connect, my DHL matchup, then DHL matchup generates a PSK, I do a TLS handshake, and now each of those become in TLS. Or we could even think, well, I create my global generated PSK on the admin queue. In most of the IO queues, I can use the global GPSK, and IOQ2, for some reason, I would like to do TLS concatenation, so I generate its own PSK. At the beginning, we can think that all these things could be possible. We did not connect the fact that each of these PSKs, to be able to be reused across more than one queue, required a unique identity for the TLS protocol to work. And look as an example at this possible case. I have a subsystem where I have two controllers, and these two controllers are connected to the same host. Okay, given I cannot have one PSK between host and C1 and another PSK between host and C2. Why? Again, because my PSK identity is defined just by the identity of the host and the identity of the subsystem. And so I cannot disambiguate the associations to different controllers. This was the problem that we highlighted when we started to implement this. The solution approach basically went to in two pieces. We had two parts, and this is what the TP8018 did. First, we defined a new per PSK unique identities. And now we are able to support unambiguously multiple scope of a PSK because we are able to associate a unique identity to a certain PSK, which is what TLS 1.3 requires. And then we decided to restrict the use cases to avoid to have to manage too many PSKs. And so we restrict the TLS generation case to the admin queue, use case number one. And then the IO queues, we reuse the PSK generated of the admin queue. So how do we do the per PSK identity? We compute a PSK digest. We use the secure hash that is associated with a PSK. And then we compute the digest as the HMAC using the PSK that we have as a key of the concatenation of the two identities. Again, the QN of the host and the QN of the controller, plus the string NVMe-oF address. This result in a bit blob, and we transform it in a base using base 64 in a ASCII printable result. Once we have computed the digest, we add the digest to the PSK identity. And so in this way, we are able to get the per PSK identity. We changed the format of the IPSK identity. So we went from format 0 to format 1. We still keep RNG for the retained PSK and identity and the generated PSK identity. Then everything is the same, but we add the digest of the PSK. And now the resulting PSK uniquely identifies the actual PSK. That is the important thing that now we achieve with the addition of the digest. So now it's possible to support add many generated PSKs and use different generated PSKs on different controllers, or use the same generated PSKs on different controllers. Can do whatever we want because now we have an identity that uniquely identifies the PSK and not just a pair of entities. Also, we get support for a functionality that we did not have before, which is called PSK rollover. Suppose that you are using a retained PSK. So you are an administrator and you configure a PSK on a host and the same PSK on a subsystem. And everything is working fine, but then you want to upgrade that PSK. You want to change it. How can you do the change? With the old definition of PSK identity, you can have only one PSK associated with that PSK identity. So really, rollover was not possible because you need to add another identity, but then how do you identify that other identity? Now that I have an ID, a PSK identity that enables to identify these two different retained PSKs, well, I'm able to do the rollover. I add a new PSK, there is its own PSK identity, both are active at the same time, and then we can roll over from the old one to the new one. So these are all the things that we have. And now if I wanted to have a PSK that works across a pair of entities, it's really not a problem. I do my DHL matchup transaction that generate one pair PSK ID PSK1, and then for my TLS, I leverage this pair of PSK and PSK identities for all my TLS connections. If instead I want to do one PSK per each association, totally fine. I define my first association, do it DHL matchup, a first pair, PSK1, PSK ID1. And I use that to set up the TLS channels on that association. I establish another association and define a new PSK and PSK ID pair. And I use that one for the TLS session on that second association. Same on a subsequent association, define a third PSK identity and PSK and I use that one for a third association on TLS, same as many times as I want. So in this way, we resolve this problem. And as we say, then we decide to simplify the use cases in which, so we do the TLS concatenation process only on the admin queue. From there, we get the generated PSK, and that now will be shared across all the IO queues of this association. Next slide.
Okay, so I'm going to talk about opportunistic TLS, the concatenation mechanism that we've shown you for how TLS uses a PSK that is generated by DHH CHAP authentication is an example of a general mechanism called opportunistic TLS. And some interesting effects showed up in implementation when we started to use it. In particular, funny thing happened in an early NVMe over TCP implementation using TLS and TLS concatenation. So the TLS concatenation design that I showed you earlier switches to TLS in the middle of a TCP stream. The following three things happen in order. DHH MAC CHAP authentication is performed in the clear during TLS PSK. During TLS PSK is used to authenticate the TLS handshake, which is another set of messages instead of TLS. And then after the TLS handshake is done, you're running TLS and TCP traffic continues under TLS encryption. This is an example of what is called opportunistic TLS. Well, that was an interesting theory. What about the practice? We had an implementer input this code and then ask what he thought was a straightforward question. What do I do with the NVMe commands that arrive during the TLS handshake? Well, if you look at the first part of this slide, that wasn't supposed to happen. You were supposed to do things in order, and only after TLS is set up do you send commands. And so our reaction was, what? That wasn't supposed to happen. The implementer's comment says, well, that's really nice, but my code did that. Now what am I supposed to do about it? Well, after a fair amount of head scratching and thinking, in 2020 hindsight, this is an example of a known problem with opportunistic TLS, that unexpected non-TLS traffic can bypass TLS handshake in progress and be processed afterwards, and the code that processes it can get confused about whether it was picked by TLS or not. It's been seen in SMTP, that's email exchange and delivery protocol, SMTP implementations of TLS. And what's really going on is under the stack, so multi-layer protocol stack tends to be very good at directing incoming traffic to the right protocol layer, and TLS is at a significantly lower protocol layer in the stack than the NVMe traffic. So we needed to do something about this, and what we settled on was something called an explicit disconnect solution. So the basic idea is to use two TCP connections. So after we generate the TLS PSK, go through that first three steps in the previous slide, we're going to remove the first TCP connection and start TLS from scratch on a second TCP connection using the TLS PSK right up front to start the TLS handshake. Now, the reason for doing this is it provides us a robust solution to that non-TLS traffic. The host can still send an NVMe command during the TLS handshake, but can still send it early, but it's going to strand that traffic on the first TCP connection, and the second TCP connection can be tightly restricted to only do the TLS handshake. So if traffic is sent during the TLS handshake, the second connection is going to close immediately because it's running strictly at the TLS layer, and that unexpected traffic is treated as bad traffic, and the TLS specifications have robust mechanisms for closing down connections when traffic that is sent shouldn't show up. So the upshot is we're going to start a first TCP connection, generate a TLS PSK. If any NVMe commands are sent other than the authentication commands, they're not going to do anything. They're going to get stranded when we drop that connection. And on the second connection, it starts up directly in TLS, running that, and any traffic that shows up will be interpreted as non-TLS traffic and will cause that connection to close. Okay, so here's what it looks like in practice. We start up with a TCP handshake, a connect. We run the DHH MAC CHAP, and generate a PSK. And that's it for this connection. The TCP connection is disconnected. If anything other than the commands necessary to do security were sent, they're going to get stranded on the sockets and torn down when the TCP connection comes down. Now we've got the generated PSK, we can now move to start setting up the actual connections that we want for the queues. So here's the setup TCP handshake, TLS, NVTCP connection request and response, and the connect command. There's the admin queue that gets repeated for each of the IO queues. And every single one of these, you see TCP handshake followed by TLS handshake. And the result is that you can't get traffic interfering because it's not possible to send any command, any NVMe command on that queue until you get all the way down to the final connect step that sets up the connection and sets up the queue. And the upshot is this is a complete sequence of how things happen in the previous diagram. You see that you get a TCP session established in the yellow arrow, which generates a PSK. The purple arrow with the dotted lines is the disconnect that first session, after which we use that PSK to set up all of the secure connections and secure channels for the admin queue and the various IO queues. The entire sequence of operations is listed on the right hand of the slide, which I will let you read in your own time afterwards. And so that completes all discussions of TP8018. We had a lot of things we had to do with TLS. And now Claudio's going to talk about usage configuration, about how to configure end systems to use these security mechanisms.
Yes, this was another kind of problem that came out when people started initial implementations of these protocols, because this protocol has some negotiation capabilities, but also we always say, well, but if you need to be secured, you need to use the protocol full stop. What do you want to negotiate? Or if the protocol is not there, you cannot use it. Or if you don't want to use it, what happens? And so on. So there was everyone understood at a certain point that we cannot just define the protocol. We need also to define specific conditions, some simple state on the endpoints, so on the host and the subsystems, that basically enable to say, okay, I'm going to use authentication, or I'm going to use TLS, or I'm going to use TLS concatenation, whatever it is, and how do I want it to be used? It has to be there, or I close the connection, or yeah, if it is there, I use it, or if it is not there, I don't use it. Still, I'm fine with setting up a connection. We need to have these things. So first of all, we establish this terminology. We define that a security mechanism, as an example, the HMHAP or TLS, can be provisioned or not provisioned. Fairly simple to understand. A security method is not provisioned if your implementation supports it, but as we said before, the HMHAP requires to be used, requires a provisioning of a key and a way to access the IDE, or a key and some verification keys. So the security mechanism is provisioned when the parameters that this security mechanism needs has been provisioned. And so it is possible to use that security mechanism, as an example, the HMHAP. Or if you configure PSK for TLS, then TLS becomes a mechanism that you can use. So in order to use any security mechanisms, you need to provision it. You need to give to these mechanisms the parameters that you have. Once a security mechanism is provisioned, the usage of these mechanisms can be disabled, permitted, or required. Disabled means no matter what the other entity does, what is the support in the fabric, I don't use it. End of story. Required means, well, no matter what is what happens in the other entity of the fabric or not, I have to use it. This is what I'm saying here. And finally, we have the permitted state, in which, say, if it is permitted, How do I get there? Well, the basic idea over there has been, why do we need a permitted state? You need a permitted state because, unfortunately, security has not been defined on day one of NVMe-over Fabric. Security has been defined after the fundamental framework for NVMe-over Fabric has been defined. So it is an add-on. It is not a basic feature of NVMe-oF implementation. Right now, NVMe-oF data implementation do not implement security, do not use security because, or maybe they are just beginning to have something because, again, security was defined later. So in order to get to a secure fabric is a place in which, okay, all my entities are provisioned, all my entities are configured to require security. And so in this way, everything has to be authenticated, the traffic is protected, no one can enter that fabric. That is a secure fabric. There is no way for that strange guy that David showed at the beginning as the intruder of the fabric can do anything. So that is the way in which you will get to a secure fabric. But in order to get there, you need to migrate your configuration. You need to move from an initial state of no security to an end state of full security. And so this is why there is the permitted state. It's something that enables a fabric administrator to go running, to basically enable security selectively on various entities of the fabric and go from an unsecured configuration to a fully secure one. And the main idea of the permitted mechanism is we look at the discovery log entry for the NVM subsystem. The host look at there, if certain fields are set, the host will use the security mechanism. Otherwise, the host will not use it. So the NVM subsystem lets the host decide. That is the permitted way. And this applies to both TLS, to all TLS, DH and matchup, and TLS concatenation. So this is the full security processing that a host or a subsystem are doing when basically they set up a TCP connection type. If TLS is provisioned and can be used, then we follow the TLS usage configuration. After successful completion of the connect command, if authentication is provisioned, then we follow the authentication only usage configuration. If instead we have also TLS and we are able to do TLS concatenation, we follow the TLS concatenation configuration. That's basically what we have to do. And so in this way, we are able to select about, okay, which of these mechanisms is being used. And the fundamental thing is, let's do an example for TLS. This is the table, so that is an example of the table that TP8025 defined. The configuration, as we said, we are looking at TLS, can be disabled. What does it mean? It means that only TCP connections without TLS with a remote entity are allowed, or can be required, which means only TCP connections with TLS with a remote entity are allowed, or can be permitted, means either TCP connection with TLS or without TLS are allowed. Everything is okay. So this is fairly straightforward what the configuration means. So let's look what this means on a subsystem. If I configure a subsystem with TLS disabled, the subsystem will close a TCP connection if a TLS handshake is initiated upon completion of the TCP handshake. Means I don't accept a TLS handshake. If TLS instead is required, then the action will be to close the TCP connection if a TLS handshake is not initiated upon completion of the TCP handshake. So if a TLS is required and after completing a TCP connection, the subsystem gets an NVMe command rather than a TLS handshake, it will close the connection. If instead a subsystem is in permitted state, it will continue all TCP connection, whether or not a TLS handshake is initiated upon completion of the TLS handshake. And what the host does, if the TLS is disabled, does not initiate TCP connection with TLS. If TLS is required, then initiate TCP connections with TLS. And if it is permitted, you have all this big blob of text, but all what this blob of text says, if TLS is permitted, you go to look at certain fields in the discovery log entry for the subsystem, and if these fields are certain values, you start in TLS. If these fields don't have certain values, you go in TCP. And what is the summary of everything here? Well, we defined, this was the background session, we defined the fundamental protocols that were able to resolve all the issues that David highlighted in the framework session. Once we began real-life experience with those, we figured out that, hey, there were some issues that still needed the solution. TP8018 and TP8025 resolve those issues. Now we are fine. Now we can properly configure security. We can use TLS transport in the proper way. The security architecture for NVMe-oF is complete and practically deployable. And that's it.
Great. Thank you, Claudio. Thank you, David. Thank you, everyone, for joining. If you all would like, the webinar will be available to view on YouTube and Bright Talk after it wraps up here, and the slides will also be available to download on the NVM Express website. Thank you all so much for joining.
Thank you.